Welcome to the 10th annual Martin Gardner Celebration of Mind. Let me introduce the speaker, George Hart, and he's going to be sharing with us his insights into using basic parallelograms to create beautiful 3D zonohedral structures, both virtual and physical. George is a sculptor and a mathematician who demonstrates unusual ways to make mathematics beautiful and just plain cool. He's retired from teaching at Stony Brook University and is a co-founder of the Museum of Mathematics in New York. And he's currently located in Canada, where internet access has been troublesome. So after his opening remarks, I'll be showing a video that he created to demonstrate some of his work. So let me now turn it over to George.
I'm just gonna sit back here and show a little video that I made. So this is a project. It's a topic that I've thought about for 20 years or more. There isn't much written about it. And about a year ago, just in the winter, I spent a month or so writing some code and exploring a little bit. And it just kind of sat in the back shelf of things I'm interested that I'll get to someday. And then about 2 or 3 weeks ago, I decided I should make a little library, and this sort of came to mind as something I should use as a sort of a mathematical basis for it. And then about a week and a half ago, someone asked me, can I make a video? Okay, can I talk for the Celebration of Mind? And I said, well, I could use this topic. So I quickly put together this video. So hopefully it's self-explanatory, and we'll let it run. And then afterwards, I'll be happy to expand on everything. It's kind of compressed. There was a lot of things I thought about including that I kind of wrote in an initial outline, then I kept crossing stuff off until it became of a manageable size. Anyway, I'll be very happy to expand on anything you see afterwards. So I guess, Fred, thank you for organizing this, and let's let the video play.
Hi, my name is George Hart. I'm a mathematician and a sculptor. I like to take mathematical ideas and apply them to the design and fabrication of geometric art. Usually what I make is intended purely for visual enjoyment, but sometimes I make things that may also have some applications. Mathematics provides a storehouse of beautiful ideas. We explore them and keep them in the back of our mind until someday we may find a use for them. So what I want to do today is explore some ideas about structures made of parallelograms, and then apply them to make a little library. So first, what is a little library? It's just a publicly accessible box of books where you, or anyone, can freely take a book or drop off a book. People make them in many shapes and sizes and place them in their front yards, or wherever, for the community to access. You'll find pictures of thousands of little libraries online. They all help spread the joy of reading. I wanted to make one for our front yard, which led me to think about possible shapes. Rectangular boxes are nicely functional, but the world of geometry provides an enormous variety of other forms that might be used. Recently I had been exploring a type of design that might be called a zonohedral surface, so I decided to make something in that family. The key idea to understand these patterns is that if I give you 2 line segments in a V shape, there's a unique way for you to fill in the V to make a parallelogram. You just add 2 new segments of the same lengths parallel to the given segments. Depending on the lengths and angle of the 2 segments I give you, you might get a rhombus, a rectangle, a square, or just a generic parallelogram. But it's always flat, lying in the same plane as the 2 original segments. Next, things get more interesting if I give you a zigzag path to start from. Each zigzag pair is a V, so you create a series of parallelograms. This is a very simple algorithm. It's basically just vector addition, but we'll want to do it lots of times from different initial zigzags. So let's code it up and see what happens. Again, we start with a zigzag and fill in the V's as parallelograms. But now the new edges give you new V's, which generate a new row of faces. You can continue the process with more zigzags and more faces, going on and on and on to make a connected surface. Plus, you can go the other way, using each zag-zig pair from the initial zigzag to work backwards. Varying the lengths and angles of the initial zigzag just bends and stretches rows or columns of faces. By the way, those rows or columns are called zones, which is where the term Zonahedron comes from. Equivalently, instead of starting from a zigzag, you can think of these surfaces as generated by one path of just the zigs plus another path of just the zags, analogous to how the x and y axes can generate a checkerboard. From this perspective, it's easy to see how bending one path produces an arch, or bending both paths can give a gracefully curved surface. From the engineering perspective, it's important to keep in mind that anything designed by this process is directly constructible by assembling flat parallelograms, which are easy to cut from wood or other sheet materials. Changing the lengths and angles of the generators allows you to control the resulting surface. If the initial paths wiggle through 3D space, the surface can be more interesting. There are lots of nice directions to explore using portions of these surfaces in architectural ways. But let me first add a new ingredient. From what I've said so far, you might expect all surfaces to look more or less like graph paper, perhaps skewed, but always having 4 quadrilaterals meeting at each vertex. To see that there are many more possibilities, let's go back to the zigzag idea, generate a portion of its surface, then pause, and add a new direction. What I've done here is insert into an existing V a degenerate zig and zag that lies right on top of itself. Because it's degenerate, it fits perfectly into the existing zigzag, but it creates 2 new V's where there had been just one. When we continue filling the V process from there, now it involves a new direction. We can choose to add new directions whenever and wherever we want. To modify that example, let's insert multiple copies of the same degenerate zag-zig into all the V's. The process continues from there with a new pattern, but it splices perfectly into the previous pattern. Note that we now see vertices of degree 3 and degree 6, so we are no longer restricted to only degree 4, like graph paper. What's happening is that if a V has an angle of 0 or 180 degrees, the parallelogram it generates has 0 area, and it's invisible. It's just a line sandwiched between other faces that are visible. So in a deeper sense, the underlying pattern actually is still a checkerboard, but the invisible faces obfuscate that simplicity and result in a richer impression. Adding and removing these degenerate parts of a zigzag give lots of design possibilities when creating zonohedral surfaces. Now, let's enrich the process in a different way, by closing the zigzag, or one of the generating paths, into a loop. It isn't surprising that one can make cylinders out of rectangles. We can also make cylindrical surfaces out of parallelograms. If you now perturb the starting zigzag loop, we can produce all sorts of sinuous surfaces. So we have many interesting possibilities, but for my little library, I thought I should start with something pretty basic. We can start with a set of V's that meet at a point and are arranged like the ribs of a half-open umbrella. Filling in the V's leads first to an expansion, and then to a contraction to another point. This particular form is well known. It's called a polar zonohedron, roughly the shape of an American football. In terms of our V-filling process, the complete surface actually continues infinitely in both directions, with degenerate faces that cross at the nodes. As an aside, I'll mention that this is completely analogous to how mathematicians think of a cone as actually an infinite double cone. But for practical constructions, we just want a finite chunk of it. When creating a polar zonohedron, as design parameters, we can vary the number of umbrella ribs and the angle of closure to make different shapes. In the limit, as the number of ribs on the umbrella increases, the shape approaches a rotated sine wave. Now, let's combine some of these ideas and see what happens if we grow a polar zonahedron for a few steps and then do the insertion trick. We'll add some additional zigs and zags that are copies of some of the original directions. When this is grown, we get a shape that's a fusion of two polar zonahedra that fit together perfectly. By analogous steps, you can create giant complexes that fit together perfectly but are entirely constructible from planar parallelograms. Or by inserting new v's this way, we get a different type of visual texture. And you can explore all kinds of variations. This one reminds me of a walrus. A close cousin to the polar zonahedron is this lovely helical ribbon surface. You can start it from a zigzag path that cuts across the surface. Or you can start it from an infinite zigzag that goes along one edge. And there are all sorts of elegant oscillating columns. All this is just a start to the many ways to play with these ideas. Part of their beauty is that they automatically have an internal coherence with parallel segments and a clear feeling of structure. But I know of almost no documentation about them. While much is written about convex polyhedra called zonohedra, there's almost nothing about this broader range of what I'm calling zonohedral surfaces. I can point you to a few 1970s publications by the Dutch architect Anton Hanegraaff, who made marvelous paper models, and some animated videos by Russell Towle from the 2006 to 2008 period. He discovered families of amazing space-filling forms he called spiralohedra. Each of these polyhedra can pack space without gaps or overlaps. And as an aside, I'll mention that when seen from the V-filling perspective, they're also fascinating for having membrane surfaces, like fins, back-to-back faces enclosing zero volume. And starting in 2007, Rob Bell had constructed a series of truly amazing art structures based on zonohedral surfaces at Burning Man. Look up Zonotopia for examples of his work. But no one seems to be exploring further in these directions currently, so I hope this video might get some of you more interested. An easy way for you to start exploring this family of designs is to use ZoneTool. It's a commercially available building construction set that allows you to make parallelograms in space easily and accurately. The balls allow for 31 directions in space, and there are struts of various lengths. So you can create your own initial zigzag and start filling it in with parallelograms. Here's a basic polar zonahedron. Here's a variation with steps. Here's a spiraling column. Here's a helical surface. Here are two connected polar zonahedra. Here's a cluster of several zonahedra. Let's move on now to the little library. After considering lots of possible designs, I thought I'd start with a basic polar zonahedron and see how that goes as a learning experience before making something more complex. Putting the rotational axis vertical with 10-fold symmetry seems about right. This is a nice balance between being round and feeling too polygonal. Cutting off roughly the bottom third allows it to have a stable base and an onion dome shape that has its widest diameter a bit up off the ground. It's straightforward to cut parallelograms very accurately from wood on a table saw. That's what I would use for a larger structure. But this little library will be small enough that I could cut the pieces with my laser cutter. I'm using 1/4 inch Baltic birch plywood. That's about 6 millimeters. It's not very thick, so I'm counting on the dome shape to give it structural integrity. The laser cutter leaves smoke marks, so I sand the front and back surfaces. Next, I bevel all the edges so they can butt together perfectly. There are slightly different dihedral angles between the faces at each level. They're easy to calculate, so I'm just careful to keep track of where each piece will go and label everything for reference. Because everything is cut very accurately, I decided I could just glue the panels edge to edge and use tape to hold everything while the glue dries. I started at the pole and worked layer by layer, waiting for the glue to dry before adding the next layer. So this grew in spurts over several days, relying on precise cuts and the tenfold symmetry to keep everything accurate. The bottom layer consists of half rhombi cut into isosceles triangles where it sits on the base. You can see I left an opening here for the door, and there's a shelf inside at the widest level. After a coat of primer, the inside is painted a light green, and the outside is painted yellow to match our house. The door is the trickiest part. I joined these panels with small biscuits for added strength, and I cut acrylic windows that fit in the openings in the panels. Then it all comes together finally when the door is attached and it starts to feel complete. Some routine cabinetry includes installing a handle and a magnetic latch. I made a sign to go with it, laser cutting letters in a whimsical font. Hopefully this will help people know what it is. Here it is, all finished. I haven't installed it yet, so it's just sitting here on a table until I install a post in the front yard for it to sit on. You can see a few details I didn't mention, like a rain gutter to keep out water and a small flagpole at the top, but fundamentally it's just a nice zonohedral surface generated by a 3D zigzag. I hope people find this to be a worthy little library, and I hope this project leads more people to explore the amazing beauty and richness of mathematical patterns and surfaces.
What software did you use for graphics?
The animations are all done in Mathematica, if that's what they mean.
I guess I could ask to follow up on that. How long did it take you to make the video and the animations?
The basic software for generating and exploring from zigzags, etc., I had written sometime last winter. But I just made animations like for my own research purposes, just for insight. I actually started making this video Sunday and finished it yesterday morning. So the actual editing, putting together the script, formatting videos, for the right size and to look neater rather than just for me to view on the screen. All that was done in the last, since Sunday. There's a question here, can you make a torus out of parallelograms? I believe you cannot. You can make sort of like a cross of two circles, but it's going to intersect itself. I don't think you can make a nice clean torus out of parallelograms in this way. But I'd love to find out otherwise. As I said, this whole topic is something which is not, it's not a topic that academic geometers or others have studied and codified as far as I know. So exactly what are the limits? I don't know. I've found there's a zillion things you can make that are really cool looking. And there's lots more I haven't sat down and followed up on yet. So I'd be curious to learn if anyone has any references or knows of other sources. The only three people I know who've really explored these sort of surfaces are the people I mentioned in the video.
Do you know if anybody's using this concept commercially to make structures?
So people have been making zonohedral structures since at least the 1970s. I mean, Steve Baer and others sort of created, there was various hippie communities with geodesic domes of various sorts. And that's when Zonohedra, I guess, began to become popular. People realized how you could make an enormous range of designs with a small inventory of parts. Compare them to, say, Buckminster Fuller's geodesic domes, where as you get larger and larger, if you want to keep it on a sphere, which was sort of part of Fuller's definition, you start to need many, many different lengths and angles to make the vertices all land up on a sphere. The idea of a zonohedra says, well, the vertices don't have to be on a sphere. They could be a little higher or lower. And then we can adjust things and have a much smaller inventory of parts. So this sort of comes out from that design philosophy in some sense.
Well, you mentioned Buckminster Fuller's constructions, and I know a number of buildings have been used as domes, for example. Is there an architectural or a structural advantage one way or the other?
I'm not an architect or an engineer, so I could say that there's probably lots of advantages to all different designs, in terms of strength or cost or whatever. The advantage to working with a fixed set of directions is that you have a small inventory of parts. So that Zoom toolkit that I showed was invented by Steve Baer around 1970, and it developed in various ways since. But you have a small number of sticks lengths, and you have only one type of ball, and you can make an enormous variety of different things. So I wrote a whole book on that, Zoom tool geometry, that has a chapter on Zonahedra. It doesn't talk about these surfaces in this way, but the beauty of that philosophy is the enormous number of different things you can make from a very small inventory of parts.
And there's another question about Mathematica and parts list, if you can look at the Q&A.
Does Mathematica allow to export a parts list for construction? Mathematica is a general programming language, so it allows you to do anything you can think of, just like any other programming language. You just have to write the code to do it. So the code that I wrote allows me to produce these structures, and it outputs the outlines of these faces so that I can laser cut them. It outputs tables of data of lengths and angles. It outputs in various other forms. I've made a lot of models with cardboard pieces where it draws them and then has little tabs on the end that I can fold the tabs and glue them together. I've done workshops with students where we build giant cardboard Zonohedra domes. And very inexpensive. If you can get cardboard free from a place that makes cardboard, that's a wonderful way to make structures for indoors quite inexpensively. Anyway, so my code is not designed as a commercial program that's easy for anyone else to use. It's just my own put together research level code where I keep trying things out and modifying it and putting together what it is that I want to explore. So it's not designed for users to just put out these pieces.
There's a question in a chat from Janine Mosley. She sees some polyhedra behind you. Can you move your camera so you can see more?
I'm wondering what polyhedra behind me. There's a bunch of different things.
Oh, there they are, yeah.
Oh, there's stuff all over the place in here. I brought, if people were curious I had shown some sculptures in the beginning. I don't know. I have those handy next to me, but my house, my life is full of models and sculptures and polyhedra. I don't know how much I want to show. But
there you go. Wow, that's great. Yeah.
I live in a highly geometric environment here. Someone mentions John Robinson's sculptures in Wales. Yeah, so John Robinson was like a sheep farmer who, after he retired, started making amazing, wonderful sculptures. Look him up. But there's many people who do sort of applying geometry and mathematics to art in many forms and to sculpture. The Bridges Conference is the sort of international research conference that focuses on connections between mathematics and art. You could look up the Bridges Conference website or Google John Robinson and find lots of examples of many things that people are doing. What I do is just my own particular connection in this between these topics.
There's a couple more questions. One, can you describe the pieces and assembly of the art pieces that you showed?
This, I assume that, correct me if I'm showing the wrong thing. So this is a sculpture made out of 30 identical pieces. I don't know if you can see, it's hard for me to in reverse camera, but there's sort of flat pieces carefully calculated to join with themselves, yet weave around themselves. This is based sort of on a stellation of the rhombic tricontahedron in some sense, but 30 identical components. And many of my sculptures have that sort of feel. I have of others that just were small enough to put as part of the introduction. So this has 60 identical pieces, laser cut and beveled and stained, and there's kind of a fun puzzle aspect to these for me to figure out how to put them together after making all the parts. I'll give a commercial for G4G's auction. So this is a preview. This one I've donated to the auction. It's my contribution to the fundraiser for the G4G. So this one you'll be able to bid on, I think, starting next week sometime soon. There will be more information about that. But this similarly is laser cut Baltic birch plywood, identical components that weave through each other, kind of go over and under in a tricky way, connect strongly to the world of puzzles in that it's a very difficult puzzle to assemble, but it's already assembled for you, glued together. So it's not a puzzle that you would take apart and put together, but I get the fun of having it as a puzzle. You just get to look at it.
And there's one more. It's a sort of a comment on a question. At first glance, from an engineering perspective, the parallelograms look a bit weaker than, say, triangles in a typical truss. If the joints were flexible and the linkages were simple poles, would these structures flex?
Yeah, so what you're saying is if you just had the edges of all those faces, you have not enough constraints to keep it rigid. There's enough degrees of freedom that the whole thing would be a mesh. If every joint was like a ball and socket joint and the struts were constrained to keep their length, but the angles are free. But because they're plates, because they're not just edges, because they're solid sheets of wood, they are internally triangulated, and then they are extremely rigid. Any convex polyhedron in this sort of way is going to be rigid in the sense, not being able to flex infinitesimally. So they are very strong as they are, but if they were just the edges, then you would just have a very flexible node. And in fact, somewhere in the middle of my video, there was a kind of an oscillating tube. And that actually was an animation of every face was a rhombus, and they were actually sort of scissoring open and closed. And if you open or close one, it sort of forces all the others. So it was illustrating that flex because the faces were changing in that one particular clip. And everything else I showed, the faces were rigid.
You might want to consider submitting one of your designs to a mechanical engineering department as a final exam to do the stress analysis at every point.
That would be fun. Nowadays, with finite element methods, you would just take the 3D model and the software would triangulate it and calculate everything for you. The complexity is, I think, too hard to do by hand, but it would be a good test of whether you have mastered the whatever software tools they're supposed to use nowadays.
Any final comments, George?
Thank you. I hope people find something inspiring and exciting. To me, mathematics is full of just amazing, beautiful ideas, and part of what I try to do is take some ideas and make them tangible for others to enjoy as well. So if I've done some of that, I feel very happy. Thank you.
Well, thanks again for your participation in your presentation. Thanks everybody else for attending, and we'll see you later on.
Bye-bye.
Bye-bye.